Hi, everybody. Welcome to our Zcash community call on this 19th of December, 2024. I'm John from Qedit. With me, Pablo, Constance, and Vivek will be presenting Zcash shielded assets. It's time, it's here, and we want to be sharing with the community what we've built and why. So let's start. The main message that I want to convey is after several years of work, we are at the stage that ZSA, Zcash shielded assets, are ready to be merged into Zcash to become a part of the Zcash protocol. Now, for those of you who don't know, it's the ability to issue assets on the Zcash blockchain and move those assets with full privacy. We have proposed and iterated with all of the community Zcash improvement proposal, ZIPs, that are now part of what is planned to go to NU7, the next network upgrade. There's several other features that you can see listed here, but the main focus of NU7 and maybe the biggest jump in the protocol altogether in Zcash is the ability to issue more than just ZEC, but those new assets. This is the result of work of several years. We first worked on the core protocol changes. Then we also implemented those changes first for the Zcash D node, and then later for Zebra node in Rust. The underlying cryptography and the proofs, the circuits, we're going to do a deep dive with Constance, who will explain exactly what are the changes and why they're needed and what we worked there. You need to know that a lot of the work that has been done to make sure that Zcash shielded assets are ready to merge have been done over the years and have been actually ready for some time, the circuits. We've also been working on features on top of those, of these core features of transfer and issuance, such as asset swaps and more. Those are coming next in next upgrades. So this is the big moment to make sure that the protocol accepts Zcash shielded assets. It comes together with these two sort of announcements. Those zips are now merged as part of the draft zips in Zcash, and we just received the results of a security audit by List Authority. I think Constance will talk about it also a little bit. This coincides. It coincides with us being able to also demonstrate this functionality on Zebra. So all our work has been replicated from Zcash D to Zebra, and now in Zebra we can show with tools that we built how to issue an asset and move it around. Basically, if we want to know what is a Zcash shielded asset, or what was this project about, the core ZSA, I'm not talking about asset swaps and other features, just the core ZSA. So it's a protocol change. It's an implementation of the circuits. It's an implementation of the node that surrounds this in Zebra, and like I said, in Zcash D. It's a set of tools to be able to create a transaction and test the entire framework. And it's also now a test net that we have running this to test, not in production and not with ZSAs, but to make sure that your node is communicating well with others. So it's also a test net. All of these, the objective is to hand them over to you, the developers, and the Zcash community in general, to see what it means to have assets that are able to move fully shielded. We want to know what you will do with this, and we already have example use cases that Vivek will present later in the call. But for now, let's do a deep dive in what were the changes that made it possible to create assets on the Zcash blockchain. So I'm going to hand it over to you, Constance.
Okay, hello everyone. I will just share my screen to do the presentation. I will present the modification in the circuit to be able to integrate ZSA. So firstly, I will present what are the different parts of the circuit that we have to modify. So in the protocol specification, on-chart protocol specification, we could see the main part of the current circuit. So the current circuit check the all node commitment integrity, the Merkle path validity, the value commitment integrity, nullifier integrity, span authority, diversified address integrity, new node commitment integrity, and two small check, which is enable span flag and enable output flags. So the main check are the first one. And we could see that when we would like to add ZSA feature into this circuit, we have to modify the node commitment equation. So we have to modify those two integrity check. We have to modify the value commitment, and we have also to modify the nullifier. So we could see that we modify a large part of the circuit by adding the ZSA features. I will not go explain all modification because it will be too long. I will firstly focus on value commitment modification. So here it is the equation for value commitment for native assets. So it is the current equation in the on-chart circuit. And here it is the new equation for non-native assets. So what are the difference between the two equations? We slightly modify the value balance. And the main modification is the fact that here we multiply the value balance by a public input via shard, and now we multiply the value balance by a private input asset base. So if we look to those two equations, we could think that the modification in the circuit will be quite slow, but in reality, it is big. It's a big modification because here we have a public input, so we could use a fixed base scalar multiplication, which is quite efficient to evaluate. And now we have a private point here, asset base, and we need to use a variable base scalar multiplication, and it will be more expensive in the circuit to perform this equation. And also this variable base scalar multiplication with this type of asset, which is a signed scalar, on this type of asset base, which is quite long, was not implemented into ILO2 directly, so we need to think about how we could implement this formula, this equation into our circuit. And last thing, for each equation we update, we would like to be sure that in our circuit, our new circuit, is able to check the validity for native and non-native transaction, and we would like to be sure that we will not reveal whether it is a native or non-native transaction into our circuit. It means that, for instance, for value commitment, because we just see the equation, we need to evaluate the value commitment with the native equation on the native input. We need to evaluate the value commitment with the non-native equation on the non-native input. And then we need to perform a multiplexer just to select the correct value commitment that we would like to keep. And we cannot perform just one of the both value commits, because otherwise it will reveal the type of the assets of the circuit, and we do not want to reveal this. So we could see that we will have a big increase in our circuit because we modify a lot of equation. And when we implement ZSA, a new feature in the zero-knowledge proof, we have two main challenges, which are the speed and the security. So we would like to have a transaction validation, which is quite speed. We do not want to, a user does not want to wait too long time to have a validated transaction. And we would like to have something which is secure. Otherwise, nobody will use our cryptocurrency. So I will explain how we reach those two goals in the ZSA implementation. So firstly, I will focus on the security part. So when we add the ZSA features in our circuit, we have some new equation, but also some new private inputs, which are called witnesses in ZK. So there are no common methodology to obtain a secure circuit. So we try to find a methodology to obtain a secure circuit. So for new witnesses, our methodology is to perform a run check for all new private inputs. So for instance, I just present his native asset in the previous slide, and we would like to check that this new input is a Boolean. And the second part of our methodology is the fact that if we have several witnesses that are related, we need to check this relation in our circuit. What it means. So in our circuit, we have two new witnesses, asset and his native assets. And we would like to check in our circuit that if asset is equal to the native asset, his native asset is equal to 1. And if asset is not equal to the native asset, his native asset is equal to 0.
Can you move to the slide? Oh, yeah. Thank you. We didn't have a second. Go ahead.
Sorry. And also about the security, now we have a lot of different cases in our circuit. We have native, non-native assets. We have dummy, split, and normal knots. I will not explain in detail what is split knots, but when we like to split a knot with native assets, we use dummy knots, and we cannot use them for non-native assets because we would like to check that the asset has been created correctly, and we use split knots to split a knot with non-native assets. So we have a lot of different cases, and we need to carefully study for all constraints in our circuit, each cases, to be sure that we have the correct constraint for each cases. And here it is just a careful study. There is no methodology to do it. We just need to implement it with carefully. So just an example about the Merkle path validity. So it is the check in the circuit that checks that the all node commitment belong to the Merkle tree. So it is the node that we would like to spend. We have to check that it belongs to the Merkle tree. So previously in our chart, so in the current implementation of Zcash, we have two types of nodes, normal node and dummy node. And if we have a normal node, we would like to check that the all node commitment belongs to the Merkle tree. If we have a dummy node, we do not want to perform this check. And how in the circuit we know if we have a normal node or a dummy node, we just check if the value of the all node is equal to 0 or not. Now we have a new type of node. So we have the split node. And for the split node, we would like to check that the node belongs to the Merkle tree because it will assert that the asset inside this node has been created correctly. So we could say maybe that if VOL is equal to 0 and split flag is equal to 0, so it is not a split flag, it is not a split node, we will not check that this node belongs to the Merkle tree. And in all other cases, we will check it. But this quick modification of the constraint will create a security flaw because now if split flag is equal to 0 and VOL is equal to 0, we not check that the validity of the all node commitment belongs to the Merkle tree, but we would like to check it. In our case, we would like for all non-native assets, we would like to check that the node belongs to the Merkle tree. So only for the dummy nodes on non-native assets, we do not want to check the path in the Merkle tree. So the correct formula is this one. Just to not check it is in the Merkle tree only if it is a native asset and VOL is equal to 0. And otherwise, we have to check the Merkle path. So we could see that it is quite easy to integrate some bugs in the circuit, and we need to really create the circuit carefully. So it is the main part of the security. And about the optimization, so we implement a first circuit, which seems quite good with security. But the main issue is the fact that so when we create a ZK circuit, we will put the private inputs, the public inputs, and the fixed inputs into what we call a layout, which is a big table. And previously, in the orchard circuit, the number of rows of this table is below 2 power 11. And if we increase this power, it will reduce a lot the efficiency of the zero knowledge proof. And the issue here is now in our new circuit, 2 power 11 rows should be near here, and we have more than 2 power 11 rows. So we observe that these columns is used a lot, and we check that which operations are performed in this column. So it is mainly some lookup run check, and it is mainly 4 and 5 bit lookup run checks that use 2 rows, and we optimize this operation just to use 1 row for each lookup run check. And another big increase in the layout is here. So here it is the evaluation of the hash of the old node commitment, and here for the new node commitment. And here it is in the first row, it is for non-native asset, and in the second row, it is for native assets. So it is, as I said previously, we perform twice each operation, one for native asset and another one for non-native assets. So it could be expensive. And we succeed to, I will go first. We succeed to improve this operation just by observing the fact that the input of the hash is quite similar for native and non-native assets. Because for native assets, for non-native assets, the input is just a concatenation of input of assets. So we could take into account the fact that we have the same prefix to evaluate the hash on the prefix just once, and then to evaluate the hash on the suffix of ZEC and suffix of ZSA, which are just a little different. So we succeed to reduce a circuit like this. The goal is to, if some part of the computation is similar for native and non-native assets, just to evaluate it on this part. But this optimization needs a big update in the circuit because previously hash was only implemented from a public initial point. So here it is public. And now we need to evaluate a hash from private point. So we need to update a lot the circuit to do that. And now we could see the optimization in the circuit. So here it is the hash previously. It is the 4 hash that we evaluate. And now we evaluate the hash on the circuit here, the hash on the circuit, the prefix here. So here it is the 2 hash on the prefix. And we have just some small rectangles for the hash on the suffix. So we gain a lot with this optimization. And also with our optimization that reduce the lookup run checks for 4 and 5 bits from 2 rows to 1 rows, we could see that we reduce a lot these columns. And here it is the limit of 2 power 11 rows. And we could see that our new circuit, optimized circuit, is below 2 power 11 rows. And now we could compare the current orchard circuit and our ZSA circuit. So we are, for the both, we are below 2 power 11 rows. And we increase a little the size of the proof. So it is a proof for 2 actions. This is an example. So increase by 2% the size of the proof. So it is not a big improvement, a big increase. For the creation time in second, we increase by 6% the creation time. On the verification time, we have a slight increase of 10%. So the increase by adding the ZSA circuit, the ZSA functionality was quite small. And just some key points to remember. So when we implement ZSA, we strive for secure, fast, and maintainable code. So we also take care of the maintainability of the code because it is very important to keep a code maintainable to easily add features later. And recently we received the security audit, and it shows that we succeed to reach those goals because so list authority says that they did not identify any issues in the ZSA protocol extension, so in the zip, in the specification, but also in the implementation of ZSA. They found the system to be well designed and clearly documented with a strong emphasis on security. So the security is here. And the repository is in scope, so it is Orchard and Halo 2 repo. are well organized and of high quality in that they adhere closely to development best practices. So we have a good implementation which will be maintainable. I will let Vivek do the demo.
Hi, everyone. Good to see you all again. As John mentioned, I had given this demo at ZCon 4 last year, but that was like with Zcash-D as the underlying node. So I'm happy to now demonstrate to you how our protocol works with the Zebra node implementation instead. So yeah, so to begin, like we have an installation instruction slide, which you can use post the webinar to build this and run this yourself. This is all like provided in the README of our repository, which is the base of this demo, which is you can find at Qedit/Zcash_tx_2. So I'll get back into these installation instructions a bit later, but I'd like to first start off with building the scenario and building a story that we can keep in mind as we run the demo. So the story that we have here is for medicine delivery. The participants of this story that we consider are a manufacturer, a purchaser, and a supplier. So the idea is that we would have like the purchaser wants to order doses for like some medicine from a manufacturer, and he has to pick those up from a supplier. And so how can like we have a possible use case where you can use Zcash shielded assets to do this in a private way. So the way we look at it is we have the manufacturer, and the manufacturer issues a Zcash shielded asset for each medicine. More specifically, you have one token of that Zcash shielded asset for every dose that the manufacturer produces. So when the purchaser purchases X doses of this medicine, the manufacturer will transfer X tokens of this Zcash shielded asset to the purchaser. So inside this transfer, the manufacturer can submit inside the memo field any necessary signatures or any other information that is required for this, like for verification subsequently. So now, when the purchaser has all these tokens that he has correspond to the medicine, the doses that he has purchased, so he wants to go and get one of these doses from a supplier. So what the purchaser can do is he can make a shielded transfer of the asset from like to the supplier. So again, the purchaser can transfer the necessary information from the manufacturer and so on in the memo field of the transaction. So once the supplier receives this token, he can verify using the memo information any checks, like he can do any checks that are needed to confirm that it's fine, and then hand over the dose. So after the dose is delivered, the supplier has this token on hand, which is sort of used up because it's corresponding to a dose of medicine that is now that has now been handed over to the purchaser. So the supplier can then burn such a token, and that moves it out of circulation, and it can no longer be used. So the idea is that this can allow the manufacturer and supplier to also easily track inventory among their medicines, since each token corresponds to a specific dose of the medicine. So yeah, coming back to the installation instructions, like I said, it's in the README of this Qedit/Zcash-TX tool. And yeah, that will be more up to date than these slides in case we make any changes going ahead. But yeah, the first step would be to install tools and dependencies, which I have already done. So I won't be doing that right now in this demo. The next step is that we build, like, so what we have done in this, for this demo for ease of use is that we've built everything inside a Docker file so that we can just run the Zebra node with just these two commands. So that's what I will do now. I will basically run the two commands that I mentioned on the slide there, build the Docker file, and then I will run the node. And so this is the Zebra node that is now running on this terminal window. So that's that. As I said, yeah, Zebra node is now running in that terminal window. The next bit is again a one-time setup that we need to do to install the Diesel CLI, which is used for the database management. So this is the one-time thing. So again, I'm not doing it right now. But the final step that we have to run our demo is that we run this specific command inside a new terminal window. So if I do that here, here we go. So then we have the complete demo that then just runs end to end, one after the other. And I will go through the stuff that comes out, and we can see how the demo works to match the specific the story that I gave in the last few minutes. So yeah, that's it. That's the running of the demo. So if we look now, so like the first step that we had was the issuing of assets. So you will see that in the demo does something called like issue 1000 assets, and that like our Zcash transaction tool immediately creates a transaction corresponding to that that specific transaction. So yeah, what we will see is that when you you can like the demo also releases the initial balances, and you can see that the balance of all these of all the assets is like for this specific asset, it's all 0. And after issuance, the first like the issuer has a balance of 1000 assets, which is what we said we were building in the transaction. So you can see that specifically in here as well. There is the balances are 0 at the start, and at the after issuance, you have a balance of 1000 in the issuer's wallet. So the next step was the transfer of assets. We, like I said, let's transfer 3 tokens corresponding to the purchaser buying 3 doses of the medicine from the manufacturer. So you will find this happening, and then you will see that so the balances after issue, as we saw before, were 1000 for the issuer and 0 for both the other parties, and now it is 997 for the issuer and 3 for the purchaser. You will be able to see the same material in here, like this, the transfer 3 tokens, the transaction gets built, the blocks get run, they get processed by Zebra, and then we see over here the balances of 997 and 3 and 0, as I showed in the screenshot. Yeah, the next step is the transfer from the purchaser to the supplier. So in the story, I said, let's say the purchaser just wants to buy 1 dose for now. So he transfers 1 token to the supplier. And so out of his 3, 1 gets transferred, this transaction gets built. And you see that we go like the issuers, like the manufacturer's balance stays the same, 997. And where the purchaser's balance was 3 and the supplier's balance was 0, it's now 2 and 1 respectively. So you can spot the same material in here. There's a transfer of 1 from the purchaser to the supplier happening over here. Again, the block gets processed over Zebra, and we go from 99730 to 997.2 and 1. And the final bit is the burning. So the supplier has this 1 token that it got, and he wants to burn this token. So again, you can run a transaction. You can create a transaction to do that in our Zcash transaction tool, as you see over here. Again, it gets processed over Zebra, and we can see at the end of this that we have a balance of 997, as was the case for a while for the manufacturer, a balance of 2 for the purchaser, and a balance of 0 now for the supplier, because this 1 has been burnt. And this is, so yeah, if just in case, like I have the same thing on screenshot here, the values of the asset base and so on will be different because we generate a new issuance key and so on each time. So these specific numbers that are there will be different, but the general idea stays the same. So yeah, that's basically the demo that we had over here. So I'd like to now hand it over to Pablo to go over the where we go from here.
Awesome. Thanks, Vivek. Thanks for the demo. So to put a little bit more context on things, so Vivek showed the demo where on the one side he got Zebra working as a validator, basically as a node, but on the other side, unlike Zcashd, Zebra is not a wallet, and Zebra does not generate the transactions. So in order to close this cycle, we created something that we call the TX tool, that is basically generating Zcash transactions. In this case, these are V6 transactions, and it cannot operate in vacuum. The TX tool need to read from the blockchain in order to filter the relevant nodes, and to do this dance of transaction generation and blockchain reading. So we have an independent tool that is used to generate these transactions that is not part of Zebra and need to be maintained separately. As you can see from this simplified dependency graph, both Zebra and TX tool are dependent on Libra Zcash, which is a significant component. Then down the line, we have Orchard ZSA. It used to be Orchard. We extended it to include the ZSA functionality. We now call it Orchard ZSA, but in fact, it can produce Orchard bundles in a backward compatible way. And in addition, it can produce Orchard ZSA bundles, which is what we are working toward at the moment. In addition, these two are dependent on a crate called Zcash node encryption and on Halo 2 gadgets. Halo 2 gadgets is part of the circuits changes are included in the Halo 2 crate, and part of the circuit changes included in the Orchard ZSA crate. I call it simplified graph because it doesn't show all the components, especially Libra Zcash is separated into many other subcomponents, which cannot be seen in this image. So for the one component that we consider completely finalized is the Orchard ZSA circuit. It is split between the Halo 2 crate and the Orchard crate. We don't expect any changes to the circuit in the foreseeable future, not even as a result from interactions with other NU7 components, which we will survey. Then, in order for this to be included in NU7, first of all, we need to make sure to include all the upstream updates. Currently, what we see that Libra Zcash moved significantly. We moved into one direction and Libra Zcash moved into different direction. We need to collect these changes and to include them in our version of Libra Zcash. There are also some changes to Zebra and Orchard ZSA from upstream, but these are relatively small comparing the changes that was done in Libra Zcash. Next, I want to discuss potential interactions with other NU7 components. So first of all, we have the two zips that describe the mechanism for ZSA. So these zips are they are in a very good form. To finalize them, we need to provide two additional changes, and these two additional changes were discussed not too long ago in the previous weeks. So the additions will include reference node for every new asset and the deterministic row computation for issued assets. These will be published as an addition to these two zips. So the graph of changes following these additions, first of all, we need to change the zips, and then the changes need to propagate from Orchard ZSA up to Libra Zcash and to Zebra and to TX tool. All of them need to be changed to adjust to these changes. Next, we have the transaction format. So the transaction format for V6 is basically the glue. It sits inside Libra Zcash, and it basically accumulates all the changes that are needed for NU7. It will require, so we created our own version of transaction V6, and we have a working version for this. But some other NU7 changes will also require interaction with the V6 transaction format. So we expect some changes around this area in Libra Zcash. Next, the proposed change for memo bundles. So memo bundles will change pretty significantly the Zcash node encryption change. And here our recommendation is to start with the Orchard ZSA implementation for Zcash node encryption, start from our PR and go forward and implement the suggested memo bundles. Once it is done here, the changes need to propagate it up to Sapling Crypto, Orchard, Libra Zcash, Zebra, and the TX tool. Next, we had a meeting this week with Shielded Labs, and we inspected potential interactions with between the network, between the NSM mechanism and Orchard ZSA. So we concluded that the interactions between the NSM mechanism and Orchard ZSA are minimal. Basically, the only place where the two interact is the transaction V6. So both sit inside the transaction V6, but besides this fact, there is not a lot of interaction between the Orchard ZSA and the network sustainability mechanism. Next, we have explicit fees and disallow V4 transactions, which are mostly concerned with Zebra, and again, not a lot of interaction with Orchard ZSA there. So these are the list of changes that are required to implement and embed NU7. Otherwise, we have time for conclusion and questions. John, if you want to add something.
Thank you, Pablo. So I think we've reviewed all the main parts of what is needed to make ZSA a reality. What is not present here on the slides is what it takes for the teams to iterate on a zip and on a component changing and needing to adapt to a component. This is a lot of ongoing engineering work at Qedit and in interaction with the different teams that we work with. I think we have reached a place of clarity in the Zcash ecosystem of how Zebra with ZSA and all the additional features in NU7 can land very soon. But this is not done yet. There's a lot of work ahead, and the deadlines are ambitious but feasible. So with that, we recommend all of you who are listening who can do it to get a hand on the demo, maybe run it and look at the TX tool and see how those steps are implemented in code. Reach out to us if you have ideas on how to extend what you're seeing. If you know where you will be using this as it becomes available as Zebra integrates this to put it in production. But you can already start playing with this and running this either on your local node or on the testnets that are about to come. And one last thing, we are with this feature, we're part of the bigger move of moving to Zebra. and we are closely monitoring the Zebra node. We're running Zebra ourselves, as I said, on testnet, but we're also looking at how Zebra with ZSA can be is interacting already today with mainnet. As you know, Zebra is on mainnet for all of the functionality of light wallets. So we believe that Zebra with ZSA will be in a very solid place when we move to when Zebra accept the merges and launch ZSA. And with that, if you have any questions that you want to ask here, please send them in the chat or raise your hand. And if you're watching this later and have questions, feel free to contact us either at the team, at Qedit. Our main point of contact is actually Vivek on the forums, or join the Arborist calls. We're very present in all of those calls. I'm gonna leave a few minutes for if questions are here. Maybe one word on asset swaps. So because we already know the future and we know that the next update to this is going to be implementing asset swaps, that includes a change in how the transactions function. So all conversations currently on moving to NU7 and having ZSA in NU7 have in mind that if we can already capture some of the changes that are required for asset swaps in this upgrade, then we will already put them in this upgrade to be future ready for asset swaps to make it into the protocol as well. Okay, seeing no direct questions here, thank you very much all who joined. Thank you all who presented. And if you have questions, as I said, feel free to contact us. This is very exciting times for the team, being able to demonstrate the fruits of this work to all of you, and we're very much looking forward to hear from all of you. Thank you very much.